Mark Harmon, Professor of Software Engineering at UCL. Mark, I think, overlapped with me at King's very briefly before he moved on to UCL. Mark is one of the most well-known and successful academics in software engineering in the UK. Very well known for his work in slicing, program slicing. And today he's going to be talking to us about another field that he's well known for, which is search-based software engineering. So I'll hand over to Mark to tell us all about that.
Thanks very much. Thanks everyone for coming. I'll try and speak for 45 minutes to allow plenty of time for questions, but I'm not very good at that. So do please ask me questions as we go along. And I'm sure you've all got other things to do at 4 o'clock, I guess it is. So I'll try very hard to keep time. But do give me the 5-minute silence on that thing. So yes, I'm at UCL. And what I'm going to talk to you today about is something called search-based software engineering. By search here we mean computational search, so things like algorithms like genetic algorithms and so on. How many people are familiar with genetic algorithms or taboo search or simulated meaning or one or other of these kind of right, how many people have never heard of those? Right, okay, great. So I'll try and include some something that will be a handshake for you guys, and I apologise if those who already know this, and probably that side of the talk will be a little bit on the dull side. I've designed the talk so that we're not going to get into a lot of technical detail, because rather than giving you a talk about one specific paper of work, I'm trying to give an overview of the whole field. So I apologise for those who really like those kind of talks where you get into Lemma 4.6 and so on. We aren't going to have that today, I'm afraid. So you probably know this, but in case you're wondering, this is where UCL is. It's I always, for most times I give this talk, it's north of, for some reason, when we're south of you guys, I guess. You must, I guess, we're here now.
Yeah.
Not west, Spring. Is it not so west? Is it more there? Anyway. And before I get into the talk, I'd just like to mention we have these COWs, which stands for CREST Open Workshops. So my centre at UCL is called CREST, which is Centre for Research on Evolution, Search and Testing. And we run these open workshops roughly once a month. And they're very much discussion-based, old school. Those who remember what old school was, old-style workshops where there is no submitted papers, there usually aren't any keynotes or any of that stuff, it's just each person gives a talk on their area, and we have lots of time for discussion. And they're usually, well, they are always on a particular topic. And they're recorded and archived, very similar to what you're doing here. So if you see any that were interesting, you can actually get the talk as well as the slides, if you see what I mean. We've had a huge number of people attend them from all over the world, in the United States as well as Europe, and obviously mostly in the UK. In total, one large conference's number of people. Since 2009, that is, so it's been going for a while. We're 40th now, I think. And it's completely free to register and attend. There is a £100 charge if you register and then subsequently don't attend, because we only have limited places and we want to discourage that kind of behaviour. And the refreshments are included. Anyway, so there is a website for this if you see CREST Open Workshop. It's very easy for people to get to, because it's just straight down the Northern Line to Euston, and then you're almost at UCL there. So enough about that. So what is SPSE? So I'm going to say SPSE rather than search-based software engineering, if I may, because it's a mouthful. So the idea is that the key here is that we want to use computational search algorithms on hard software engineering problems. And by search, we don't really mean these kinds of search. So you could think of those as an extreme case. They're kind of potentially exhaustive searches, and at the other end of the extreme, we might imagine picking one at random is another kind of search. What we're really talking about is the sweet spot in between those two extremes. So where you have a search base that has some structure to it, you can use computational search to find reasonably good solutions. They may not be the global optima, but they may be good enough for your engineering task in hand. So this is what search-based software engineering is. You can think of it in terms of the intersection between search-based optimization, which has been a topic of research for at least 3 or 4 decades, and software engineering. So on one level, it's nothing special really. It's just the application of computational search to software engineering. But through this talk, I'll try and make some cases to explain why it's not merely an arbitrary intersection, but something that might make sense as a discipline in its own right. So the reason we're interested in that is because we want search techniques guided by some kind of fitness. So all those things which count as search-based software engineering are software engineering problems where you have an identifiable fitness problem. But the particular algorithm you use is completely agnostic. So you might use any and all of these kinds of algorithms. And we include things like exact optimization techniques and greedy techniques where the fitness function might be either a little bit ill-defined or not quite the same as the fitness in these cases, or where the search may not actually be a metaheuristic search, but maybe an exact optimization. And in this talk, I'm going to focus a lot on genetic programming, actually, as it happens. Traditionally, there's been a lot more work in these other techniques, but more recently there's been a lot of work on genetic programming for software engineering problems. And I think this is quite exciting because it allows us to actually manipulate the engineering material itself rather than the broader software engineering artifacts. So what's the motivation? First of all, I want to convince you that it makes sense to apply computational search to software engineering. And maybe I'll do a quick check of hands. Honestly now, how many people think it does make sense already? How many people think it doesn't make sense?
It doesn't.
It does not make sense to use computational search. So things that people might say are, but these algorithms are stochastic, you know, but software has to be correct. So how can you use a stochastic algorithm? You know? Or another thing people might say is, well, you can't define fitness functions for most software engineering problems because it's like a logical problem. It's just a Boolean yes or no. Anybody think like that?
I'm agnostic.
Agnostic. How many people are agnostic? Okay, great. Okay, so I won't spend too long on that. in the early days of SPSE, this field really sort of took off around the turn of the millennium. I really had to spend a lot of time convincing people of this, and many people in the audience were very hostile to the very idea that you could use computational search for software engineering problems. That's less so now. So I never know quite how long to spend on this, but the kinds of things I hear software engineers say at software engineering conferences are these kinds of things. So they talk about the concerns not just being technical ones, but also business ones, and these kind of have some kind of complicated interplay with the technical concerns. Or they say things like, well, there's risk, particularly in the early phases of the life cycle of software projects, there's a lot of risk that needs to be managed somehow. In the design area, people will often still actually regularly talk about cohesion and coupling. Ideas have been with us since the 70s. And in software testing, a field I'm particularly active in, we often realise now that finding bugs in software is really not that hard. The problem is finding important bugs with the fewest test cases. So anybody can find bugs, but can we find the nasty ones with the least effort? And if we're interested in refactoring or some kind of measurement of software, then we might want to have a bunch of metrics according to which we want to improve the system. Now, all of these different questions arise at different phases of the life cycle, or different software engineering activities are associated with them, but all of them have actually been addressed in the SPSE literature. So I think it's fair to say that this is an approach to software engineering that's achieved very wide coverage. A large number of topics have been attacked, and they're all apparently from very different areas, but they are all formulatable as optimization problems. I'd like to skip these slides. Oh, good, I have. Right, great. Okay, so this has made this area be quite popular, and there's been quite a dramatic rise in the number of publications in the area. That graph there is a graph of the number of new papers every year, not the cumulative. The cumulative one is actually exponential. So as you can see, the number of new papers each year is rising. We did this study in 2012, so 2011 is actually an underestimate. And in terms of the geographic distribution of researchers in this area, it's quite interesting to note that this is one of the areas where the UK has a strong lead. This was also done in 2012. The USA's share is now roughly equal to the UK's, and China and Brazil have particularly picked up a lot. But it's still something which the UK has some strong leadership in. And if we look at that geographic spread in terms of countries, then anywhere you can actually see on that map has some SPSE researchers active in it. So these light yellow ones, it might only be 1 or 2 people, whereas these dark red ones, you might have several hundred people, but nonetheless, most of the globe is covered, and certainly every continent is.
You won't promise there are lots of them in Alaska, though?
I don't know. I think when I colour in a country, it could be there are none in Alaska, but there are, it's like the statistician who drowns in a pond of average depth 6 inches, I'm not aware of any in Alaska actually, but since Alaska's now US, it just gets stamped SBSE done here, I think we talked about this, didn't we? I think I showed you that slide. I'm going backwards. Right, yes, right, I was pressing the backwards button. So there's a number of places where people publish this kind of work, all the usual software engineering venues, but also there have been a number of special issues in these journals here, and there's an international symposium on the area, and lots of the countries have their own local symposiums. So there's one in Brazil, been going for 4 or 5 years now, there's one in China, been going for 4 years, and just this year there was the first North American symposium on SBSE, so another underrepresented part of the globe has its own. And there are also workshops on specific sub-areas of SBSE, so search-based software engineering for testing, and this one's for modelling. So this is combining modelling and SBSE. For some reason it's turned out to be very, very popular in Brazil. Is anyone from Brazil here? Okay, well, if you're interested, there are a couple of surveys about how this community really took off in Brazil. In total, there are about 1,600 authors in the area, and there is an SBSE repository that aims to have 100% precision and recall. It's managed by a human, so it uses artificial intelligence, and that means it's got pretty good precision and recall. So the goal of that repository is to contain every single paper and nothing else on SBSE.
So it's too late to get into this area now.
Yeah, shall we all go? No, actually, the thing I showed you earlier is the immense coverage, and that means that it's very generically applicable, but there's an awful lot of software engineering problems out there still not covered. So there's still plenty of areas where there's yet to be the first paper in this area, and at the annual conference there are probably about a third of the papers are first-time research problems being introduced to the community, and about 2/3 are work on existing problem areas, which I think is quite healthy, and that's a good balance. So in terms of the topic areas, half is about testing. And it was the case that almost all of it was testing, and then gradually these pieces of the cake have grown bigger, and now things have stabilised at about 50. For the last 5 years, it's been 50% testing and 50% everything else. And actually, that's about the same as the proportion of papers on software engineering as a whole. If you go to any of the main software engineering conferences, about half the work is on testing. So it's reached a kind of a saturation level that mirrors software engineering as a whole. But if I just take this little piece of the pie here, so the 5% of others, and just give you some idea of the breadth. So all of these areas have at least one, actually I think usually more than one, usually a handful at least of papers on them. And I won't attempt to cover all these areas now. I've done a survey of the areas, so I hope I know enough to at least explain a little bit about what's been done in each of those areas. So if any of them are interesting to you, can you see those at the back, those topics? Yeah. So if any of those are interesting to you, they're in alphabetical order. So if you can't see your topic area in the list, I did this particular slide a couple of years ago, so do tell me. It might be that, and also I can't fit them all in those. So just an indicative list, So if you see any that are interesting to you, afterwards we could talk about what's been done in that area. Or if you've got any burning questions now, I can particular area like what's been done in that area.
Actually, I have a burning question there. A good part of software engineering is human activity, and particularly how humans, in the way they design software, can construct problems for future users and so on. I'm thinking around value-centered design type of problems. Is there any sort of search-based SBSE type of problem space?
I think I can see where you're coming from. So the perception of computational search algorithms is because you have to have a fitness function, that's a great key to automating search. But what about where's the human in that loop? The nice thing is that, and also perhaps some of the software engineering questions are slightly more aesthetic, like what's a good design? The good news is that the aesthetic component can be taken into account by having humans contribute towards the fitness computation. And the evolutionary algorithms, people call this interactive evolution, where the humans are contributing to the computation of fitness. So in that sense, the human is also guiding the search, and part of the search is automated. So there's a very natural way to include the human in the loop. And this has been exploited in SBSE in the area of design, where, for example, there's work by Chris Simmons at the University of West of England, where he's looked at ways in which you can incorporate human judgment of what makes a design attractive as part of the fitness for finding improved software architectures and improved software design. So yes, it does fit, but you're right to raise the question, because the feeling is, well, what if you can't formulate what you want as a fitness function? And the nice thing is you can kind of discover the implicit fitness function in people's head without having to actually name it and write an equation for it, which is quite attractive, I think. So if you're interested in the area and what I've said sparks an interest to find out more, then there is a tutorial and there is a survey. So the tutorial is ideal if you haven't heard of the area before, or you've got a student, maybe a master's student doing a project, and you want to say, have a read of this, see what you can do. It takes you from the point where you don't know anything about SPSE to the point where you're ready to write your first research paper. So it's ideal for a speculative MSc project where you've got a reasonably good student. You think, well, let's see what they can do with this. Give them the paper, ask them to read it, and then say, think about how you could make a computational search problem out of that. On the other hand, if you've got a PhD student or someone a bit more further down the food chain, and they want to know, well, what has been achieved in this area, then there is a survey. It's a little bit out of date now, 2012, but it gives a reasonable coverage. Oh, and there's only one tutorial I'm aware of, and there are several surveys, but there's only one in ACM surveys, I think, so you don't need to remember the titles. That should do the job on Google. So I wanted to just very quickly run through a few examples just to give you a sense of this breadth. And I'm going to do this relatively quickly because I don't want to spend too long on this, but to try and speed it up, what I've done is, in case anyone's interested, here are the different computational search algorithms. If you're not interested in that, don't worry, it's not important. If you are, then that's just for extra information. And here's some typical software engineering activities, each of which would have its own conference. So, sort of sub-area of software engineering in its own right. So, for example, taking requirements, these three algorithms have been used for this sort of problem, and this is often called the next release problem. So the optimization problem is which requirements should go into the next release of the system. And this has been attacked since 2001, the first paper to call it this problem. I'm going to just focus in on this multi-objective version, which appeared in 2007. This is data from Motorola, and the score is their customers' estimated satisfaction of a particular set of requirements for mobile phone handset, and the cost is the estimated cost. And I've inverted it so that both objectives are maximising. So essentially, solutions out to this part of the graph are better. And the thing we notice is that SPSE is very well suited to this kind of cost-value trade-off. So anywhere where we've got a problem where we can measure the cost and we can measure the value, we can use a multi-objective search to get this Pareto front, which shows us the trade-off. So each of these circles represents a solution to the problem. So in this case, it's a set of requirements for the next release, and we can read off what the cost and value of that would be. Now, both of these are estimates, and there's been a whole lot of work on how we turn that telescope around and use this to improve the estimation quality. But this particular work is assuming that we somehow believe in these estimates. But if you don't believe in them, you'd be right to be sceptical, because software engineering estimates are somewhere between London builders and the stock market in terms of accuracy. So if you don't have to take on trust these estimates, is what I'm saying. But if you do, if you've arrived at a position where you believe these estimates have some truth to them, then you can get this Pareto front, and it shows you where you get your trade-off point. So there wouldn't be much point in having a solution here, for example, because you could hugely increase your customer satisfaction with very little extra cost. And similarly, there wouldn't be much point in pushing to a solution from here down to here, because you're going to incur an enormous extra cost to get that little bit of extra customer satisfaction. This is just illustrating what happens if you do a random search to show that this Pareto front is the intelligence in the search is genuinely doing something for us. So cost-value trade-offs, that's nice. If we move fast forward to software testing, then test suite optimization has been a problem that's been very widely attacked. And interestingly here, we get a very similar problem. So we have cost again, but cost this time is the cost of executing the test suite. And the value is how much of the previous fault history can we cover, and how much of the overall software itself can we cover. So we've got a three-dimensional search space. And we get exactly that same kind of trade-off behavior that you see with Pareto optimality, that there's a sort of tipping point around here. And that could be used, for example, to inform us in our decision making. If this turns out to be exactly 8 hours, then that's good, because it means we could do an overnight build and we could get most of the faults covered and most of the new code covered in an overnight build. But if this turns out to be 8 hours, then there's a case to be made to say that we occasionally need to do a different kind of a build process that's not an overnight build. So it doesn't tell us necessarily, it can tell us which test to use, but it can also give us insight into the overall testing process. The interesting, just to mention, this work has received some take-up in industry. So, for example, Google have deployed this approach in their test optimization, and IBM had a problem where they were doing smoke testing. So within 1 hour of committing a putative commit to the system, can we see if it smokes? Can we find something that indicates a fault and then take the commit back? And the problem there was they had a regression test suite that takes 7 weeks to run. So if you want to smoke test in an hour, you either pick at random a very small subset of test cases, but that might be a very suboptimal choice, or you optimize the test suite such that in that 1 hour you get the maximum bang for your buck. The trouble is, optimizing a test suite that takes an enormous test suite, so just the optimization algorithm itself could take more than an hour. So that's a bit disappointing. So your optimization algorithm now has to be fast too. The good news is, these algorithms, as those who put their hands up when I asked about evolutionary algorithms will know, these algorithms are very, very parallelizable, very naturally so. A genetic algorithm, for example, has a population of candidate solutions. And that population, every individual gets evaluated using exactly the same Fitness function. So it naturally parallelizes. And what we found in this work with IBM was that we could use GPU devices. So the graphics card you have in your computer already has sometimes hundreds of processors on it. Now those processors are geared towards doing graphics computation. But it turns out that this problem can be formulated for a graphics card such that you can use a graphics card to get you very, very cheap optimization. So we're getting speed ups of 20 and 30 times faster. And again, the speed up, these are the size of the programs to which it's applied, and the speed up gets better as we go across. So the take-home message here is that we can find faults faster, and even if the optimization algorithm itself can be quite slow, we can actually parallelize it and use quite cheap parallelization technology to do so. So actually regression testing is all about optimization. You have a new release of the system and you want to get the maximum amount of testing done in the smallest amount of time. So one thing that's interesting, I think, is that from a software engineering point of view, how many people here are software engineers, by the way? Who would self-identify as software engineer? Come on, don't be ashamed. Only 3 people. I said, well, everyone else is not very kind of you to come today to a software engineering talk. Probably in your area this happens too, right? So software engineering in the 70s, there was one conference, and everybody went to that. Now there are 25 conferences in all the different sub-areas. And it feels like all of us are doing different sort of sub-areas, so it's fractured, you know, and so we feel a bit alone. There are people who do requirements work, there are people who do software testing work, there are people who do design work, and they all go to different conferences. And so Tony would go to models probably, right, because he's a software design person. Who else is a software? What's your area?
Models and requirements.
So you go to models as well. Who else is a software? Testing. So you go to ICST, CAV, ISTA maybe, yeah. So, and probably you wouldn't ever go to models, and you probably wouldn't ever go to ISTA, right? So you know, we're all in these separate silos. But the thing is, if we formulate these problems as search problems, then we notice that this requirements problem was a cost-value trade-off, where the solution set could be represented as a bit set. Bit set if the requirement is in, not set if it's not in. Very simplest possible representation you could imagine. And in optimizing testing, we have a set of test cases, and we wanted to say which set of tests we're going to run. Once again, bit set. Bit set 1 if the test case is in, 0 if it's out. And the fitness functions are measuring cost and value. They're different costs and values, but the representation and the formulation of the problem is identical. So when we think of these people at their different conferences, thinking they've got nothing in common, if we pull the plug on this sea of illusion, you see, we can see that actually, if we had a foundation in software optimization, then we can see that actually there are these foundational connections between these areas that bring back a community that was once all alone and now could be, in some kind of Zen sense, maybe it's all one. So I think that's kind of attractive. So SPSE is a way of providing a unifying framework for a very fractured discipline, I think. And so at this point you might say, well, you know, this is all well and good, right? Particularly the people who know about computational search algorithms are probably thinking, yeah, but this is just another application of computational search, right? I mean, you can have search-based X, right? There are people who've done genetic algorithms for mechanical engineering, civil engineering. So what's so special? What's so special about search-based software engineering? Isn't it just another application, another instantiation? I did address this question in a talk at ETABS, but I want to just briefly cover this question now. So essentially I want to answer the question, what makes software engineering ideal? What makes it the killer application for these search-based algorithms? So the difference, I think, that's quite obvious, it's staring us in the face, but it's an important one, is that if I'm calculating fitness in a physical engineering space, then the cost of evaluating a fitness function could be very high. But if I'm evaluating fitness where our engineering, it's staring us in the face, we're the only engineering discipline where our engineering material has almost zero cost of replication. So the cost of evaluating fitness for a putative software engineering solution, our engineering material is so cheap to produce, at least in the sense of evaluating fitness. So that's one very, very important difference. And another important difference is to do with the way we model fitness. So if we think of something like an engine design, so Boeing have used genetic algorithms to model engines, and they have optimization goals just like us, so they might try and maximize the compression and minimize the fuel consumption. But in order to do that, they first of all have to make a model in physics of the real world, and then on top of that model, in order to evaluate fitness, they have to write a simulation, because they can't build the engine just to calculate fitness for one possible engine design, so they have to do it all in software. So we could actually argue that they're already doing search-based software engineering, because their fitness is not computed on an engine, their fitness is computed on a simulation of a model of an engine. And that introduces two possible differences, if you will. So if this is completely not possible to view from the back of the room, I'm sure, but what this is the program dot drawn using the program dot as a dynamics graph. And we can use our design goals to apply to those kind of design structures to maximize the cohesion of the module clustering, the modularization, if you will, and minimize the coupling between modules. So just as they've got optimization goals, so have we. But we compute those on the software itself. So we're computing fitness directly on that graph structure. If we say this module goes in this cluster, then that's applying to the engineering artifact itself. If I generate a test case, I'm generating it based on the execution on the real software system. And the computation of the fitness costs as much as running the program once. So when we move from this traditional engineering world with physical engineering artifacts to a world with virtual engineering artifacts, we don't have to always model the real world. We don't have to build a simulation of that model. We calculate our fitness directly. Not in every case, but in many cases we can. And that means that we can do a hell of a lot more optimization. Ultimately, because the optimization technology is itself built out of the same engineering material, software, we could take our product and put the optimization inside the deployed software, so it now becomes adaptive. So that's another huge win for this particular area that you wouldn't imagine happening with an engine design. If it was adaptive in any sense, it would almost certainly be the software inside the engine that was doing the adaptivity. So, what I hope I've convinced you at this point is, A, there is a large coverage of software engineering topics, and B, the idea of applying computational search to software engineering problems is not one that's just arbitrary. This is the killer application for computational search, which is itself a software technology and therefore could be deployed into the software to give us real-time adaptivity. So in the last part of the talk, I'd like to look at where next for this area of search-based software engineering. How long have I got left?
20 minutes.
Great, okay, so I should have enough time to just say a few things which are currently happening and we'll look to for the future. So one thing I'm very interested in is the idea of coevolution. So coevolution is where you're trying to evolve a fitter solution to the problem, but the environment in which you're evolving could be changing as well. Or there might be multiple actors in the space in which you're optimizing, and they each affect the fitness of the other. So you've got multiply evolving populations of solutions. And this fits software testing very well, because testing can be thought of as having a predator-prey kind of nature to it. So the testing technique itself is a predator, and the bugs are the prey. Okay? This naturally fits a co-evolutionary model. If we imagine, again, I use a gecko because gecko is the main conference, but this is really an analogy here. Okay? This is not what a testing tool really looks like, but it kind of does serve. So imagine the testing tool is that's gecko, and here's the bugs. Then normally we might have a situation where our testing tool is reasonably good at catching bugs. But the trouble is, testing tools are often very good at catching certain kinds of bugs. So what we might do is try and find bugs which are particularly hard to find for the testing tool. So let's evolve the bugs so we can simulate the faults. It's an area called mutation testing. And then we try and find those faults which are particularly hard for this particular testing approach to find. So now, suddenly, the testing tool doesn't look so good. And people have argued that that's all well and good, but all you're really telling is, are you telling whether these faults are really hard to find, or are you telling whether this is a poor testing tool? But what if we now evolve the testing techniques as well? So now we evolve the testing techniques to be better at catching bugs for which it was originally hard to test. So now, what we're really doing here is we're co-evolving two populations. We have a testing approach, maybe test data or a test strategy, and we have these mutants, these versions of the programs with a fault in, perhaps with multiple faults in which can mask each other. And if we evolve both simultaneously, then in theory we could get bugs which are very hard to find, which are useful in themselves, and we get test data which is good at finding bugs which are very hard to find. So this is one way in which co-evolution might be used to good effect in software engineering. There are many others, but this is just one illustration.
But
Yes?
if you have co-evolution, there's no guaranteed convergence. You may have a cyclical behavior.
You may. So what you may get is what's called metastable solutions. So you have test cases which are very suboptimal but good at catching these kind of bugs. And these bugs here are very good at being, they're quite good at being evaded, but every nearby state you get to either produces a big decrease in the fitness, and therefore you end up in this metastable state. And that's where the current research is, if you will, in co-evolution. That's the kinds of problems that we want to have so that we can be at the state of the art. And then I personally believe there are ways to solve those problems, but that's, if I just said to you, and we can all do it out of the box and off you go, bish, 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 implement and it's done, then it wouldn't be exciting. It's those kinds of problems that make this interesting. How do you ensure that your co-evolution doesn't get stuck in one of these metastable states? I have no evidence to suggest to you that that's an easy problem to solve at all. It may turn out to be a very hard problem to solve. So that's what I was just presenting. Although people have toyed with this idea, nobody's actually really got a compelling implementation of co-evolutionary mutation testing at this point. So this is an idea, but it isn't implemented. If we move on to an area where there is a bit more implementation, then genetic algorithms, actually mostly genetic programming, has turned out to be very, very effective in an area called program repair. So this is where you say, I found a bug and I want to fix it automatically. It's quite challenging to find all the bugs in the system. In fact, it's undecidable, so it would be more challenging. But even finding tricky bugs is hard. But imagine fixing bugs that you found. That's kind of even more exciting in a way. And there has been work on this area. In particular, there's Claire LeGuess, who's now at Carnegie Mellon, and Wes Weimer at Virginia, and Stephanie Forrest, who's at the University of New Mexico, have a very nice system called GenProp, which generates patches automatically for software systems. And this work was very, very influential and led to a big explosion of interest in automated program repair. More recently, that's been generalized to an idea of improving programs in general. So rather than trying to repair bugs, let's try and